Good day, everybody. I hope you are having an absolutely lovely one. I know I am, and it's only going to get better in a few minutes here. My name is Tim Sylvia. I am an editor with PV Magazine USA, and I will be your moderator for today's webinar, Chasing the Sun, Advanced Analysis for Innovative PV Materials. Joining me today are a group of excellent presenters, Christelle Mafina, UVS/TEA Product Manager at Perkin Elmer, Lucy Jenner, Industrial Segment Manager at Perkin Elmer, Dr. Gernot Orensky, Division Manager for Sustainable Polymer Solutions at the Polymer Competence Center Leeuwen, and Peter Van Nieneten, R&D Director at OMT Solutions. Before we hop into the presentation, we have a little bit of housekeeping to take care of. As you may have just noticed, each of our speakers was kind enough to turn their camera on during the introduction. You'll be seeing them throughout their presentations and throughout the Q&A after. Due to some unfortunate technical difficulties, you will not be seeing me as you typically would, but we hope that our presenters will be able to be sufficient for you. So this webinar will consist of a brief presentation with an audience Q&A session at the end, though you are free to submit any questions you may have at any time during the presentations. Due to time constraints, we may not have time to address every single question, but we will certainly attempt to. If you have any technical difficulties during the webinar, try refreshing your webpage. If problems persist, shoot us a message and we will work to resolve it. In addition to myself, my colleague Beatrice is waiting in the wings to assist with any difficulties. Okay. Now that the housekeeping is all taken care of, let's switch our focus back to the topic at hand, and that is advanced analysis for innovative PV materials. It's a pretty all-encompassing topic, and there are a couple different angles that each of our presenters are going to get into today. But kind of on the big picture, the solar industry is no stranger to complex political, regulatory, and supply chain hurdles. From material shortages to tariffs, both real and threatened, these challenges are often used as foundations for arguments against the validity of the resource. However, since 2020, solar power has risen to become the cheapest form of energy on the planet. Scientific and commercial progress remains buoyant, with an increasing number of solar farms progressing despite the ever-changing challenges they face. Innovative breakthroughs in key materials like glasses, silicon, and polymers are driving the technology forward. Scientists rely on analytical solutions which can test for the desired properties needed for solar components, including cells, wafers, and interconnectors. To better understand where the future of solar module innovation is headed from a variety of different technological standpoints and the testing that is going to enable this innovation and progress, I'm going to turn it over now to the first of our presenters, Lucy. Lucy, the floor is yours.
All right, thank you. Right, so to kick off, actually, we've got a video to play for you. This video really sets the scene nicely, I think, for this webinar, as it places solar firmly in the context of renewable energy generation and storage. And I'll be delving into those topics in a little more detail after we watch. So over to the video.
At Perkin Elmer, we're passionate about sustainability. In renewable energy generation and storage, as well as recycling, we're leading the way with analytical technologies which empower sustainability and helps our customers to 1. Improve the purity of lithium-ion chemicals and materials for safer, lighter, and longer-lasting electronic vehicles. 2. Test advanced materials and nanomaterials for ever better solar panel technology. 3. Analyze in-service lubricants and coolants to keep things running smoothly. And 4. Identify and characterize recycled materials to nourish the growing circular economy. Without a doubt, battery technology has a pivotal role to play as alternative energy generation powers more of our world. The manufacturing of new and more efficient batteries is being fueled by research and development, with production improvements to assure the quality and safety of components and end products alike. Cutting-edge analytical technology is needed at every step to test individual battery components, such as electrode materials, separators, and electrolytes. To improve battery characteristics and safety, we can help you better understand the state of materials inside the battery over its lifetime, so you can explore renewable energy generation, such as solar and wind, and accelerate the development of energy storage technology in battery development. Our instrumentation can analyze a comprehensive range of chemicals, gases, and materials, from elementals to polymers, to help move your research forward. Around the world, we're committed to providing groundbreaking solutions and forging alliances for a safer, healthier, and more sustainable world.
Okay. So solar is the most abundant and fastest growing renewable technology. It's diverse and it's both exciting and challenging, as I'm sure those of you working directly in it know only too well. There's no shortage of hurdles, from regulations to supply chains. However, since 2020 and the latest International Energy Agency report, the IRENA report, we now know that solar is the cheapest form of energy on the planet. Of the wind, solar, and other renewables, nearly 2/3, 62%, were cheaper than the cheapest new fossil fuel. So solar has a lot to be proud of. Its rapid growth has driven economies of scale that make it ever more attractive for a variety of energy applications. Scientific and commercial progress, the work that many of you are no doubt undertaking every day, needs innovative breakthroughs in key materials like glass, silicon, and polymers. And we're hearing from our customers that they need to test for the desired properties for their solar components, including cells, wafers, and interconnections. To make these advances, labs need the right instrumentation and reliable services and support to accelerate their R&D. And of course, that then helps manufacturers to achieve the high PV cell performance that they need to stay competitive. That concludes the introduction. I'll now hand over to Gernot Oreski to continue.
So, hello everybody, thanks for the introduction. I would like to start with some thoughts about polymer testing, especially for polymers which are used in PV modules. So, we already heard the PV market is very strong. It is growing very strong every year. It's highly competitive and we have an enormous cost pressure in the market as well. What is interesting to observe in the last 2-3 years, a lot of new, let's say, technologies and materials and module designs were launched on the market. And they had different reasons. I would say the biggest and most important reasons is always decrease of cost, but also to improve the performance. But also sometimes, let's say, new developments have been driven by new technological requirements or, for example, sustainability or legal regulations. So what kind of changes in PV module architecture and materials are we talking of? So what we've seen is the increase in wafer size, for example. We also see an increase in module size, but the cells itself got cut in half or more parts. We see different new approaches for interconnection, like, for example, shingling modules or the multi-wire interconnection approach, or like the structured foils for the back contacted cells. We see a big increase in bifacial module technology, especially double glass modules. On the polymer side, we see new polyolefin encapsulant entering the market, but also on the backsheets, we see new architectures, for example, co-extruded backsheets based on polypropylene or just coated polyester films. You can take a closer look on this in the IEA Task 13 report that was published last year and take a look at these changes in detail. Next to these changes, we also see different use of PV and especially integration of PV in different other areas. For example, like BIPV, building integration, is quite known. But in recent years, we saw a broad or really big increase in floating PV applications on sea, but also like lakes. We see the integration of PV in agricultural land, but also in transport infrastructure, or on a smaller scale also, for example, to integrate it into electric vehicles and therefore increase the range of such a car. So what's the challenge with all of these new technologies, all of these new integrations and new materials? The challenge, to my opinion, lies in compatibility. When you change like one component of a PV module, you change the whole basic chemistry within a PV module, and therefore this introduces one, let's say, this could introduce, for example, some sort of compatibility issues. I'm especially talking about adhesion delamination problems. I'm talking about discoloration problems, but also corrosion with all these new interconnection technologies entering the market. And we may observe new degradation mechanisms. Like in the past, like 12 years ago, we had a big deal about PID, potentially induced degradation. A few years ago, backsheet cracking appeared out of the nothing. So all the stuff, all these new degradation mechanisms occurred after some years in the field, and we couldn't predict them by indoor testing, by accelerated weathering testing, or just some standard tests that we do in the lab. Because usually our test methods and standards lack, let's say, are in constant need of adaptations because they're always behind, let's say, current developments. And with that, I want to show you why is it actually important to know your materials, especially the polymers in the PV module. Here I will focus on encapsulant degradation, and this is a work that one of my co-workers, Chiara Barretta, has done in the last years in a European project. So first, I'm aware that not everybody of you is a polymer engineer or a polymer scientist. So be aware that when we are talking about encapsulants, especially EVA encapsulants, it's not a single material where we just have EVA polymers. Usually encapsulants are consisting, to the biggest part of these polymer chains, but all of them have additives and stabilizers in it. And this mixture, this cocktail of raw material and additives actually define the lifetime of a PV module and the stability of like the encapsulant itself. And like what you can see here on this thermal desorption gas chromatography coupled with mass spectrometry result is that we have different kind of additives in EVA usually. So we have the crosslinker, that is a peroxide. We have antioxidants. We have a cross-linking initiator, usually. We have an adhesion promoter, and we have an UV absorber. And some of these additives are actually consumed either during processing, like you don't find peroxide, cross-linker, or adhesion promoter after proper processing anymore. But it also happens that due to aging, due to UV exposure, for example, antioxidants or UV absorbers are consumed. And in the next slides, I will just show you how this affects PV module, the power loss of a PV module. So this is a study we did on mini modules where we exposed these modules to 3 different lab tests. So like a damp heat test for 2000 hours, a dry UV test with the maximum UV dosage of 500 kilowatt hours, and then a combined UV damp heat test up to 250 kilowatt hours of UV dosage. Then we dismantled the modules and analyzed the encapsulant on 3 different positions. So first, right in front of the cell, second, right above the backsheet, and then third, we took some material that was squeezed out during module lamination. So that was outside the glass, directly exposed to the stresses. And what we found is like, okay, after UV damp heat test, this module lost about 5% of its initial power. After damp heat test, we didn't observe any, let's say, power loss, and a slight power loss was observed just after the UV test. What we especially saw decrease was the short circuit current that is usually associated with discoloration or cell cracks. So we took a closer look and did an additive analysis. So to check, okay, which additives are still present after these tests. And first, what you see, UV damp heat test, where we lost the power, a lot of the antioxidant, or in all cases, the antioxidant was not visible at each position. We also see damp heat actually does not do any damage to EVA material. So all the absorbers, all the antioxidants are still present. UV has some effect on the antioxidant. So how is this related to the power loss? Let's take a look to the right. You see the yellowness index measured for these different materials. So like above the backsheet, and we see strongest yellowing was after UV damp heat test, followed by damp heat test. Usually, or let's say, how is this yellowing, was it formed? And the thing is, actually the yellowing after damp heat test is different than after these UV tests, because yellowing after damp heat test is just at the interface of the backsheet and the encapsulant, but not of the EVA encapsulant itself. Therefore, we don't have any power loss. But when we UV expose the samples, actually the encapsulant discolorates, and this discoloration is actually correlated to degradation products of the antioxidants. And the strongest, let's say, discoloration you usually find where you don't have any antioxidants left anymore in your PV module, causing this degradation mechanism. Let's take a closer look. How is the material degraded? And the interesting finding was, apart from the yellowing, the EVA, the encapsulant in the PV module, is not degraded at all. So we don't see any change in oxidation index. We don't see any change in infrared spectra or in other measurements. We only saw significant changes of the material of the EVA outside that was not shielded by the glass, because there the UV actually did its job and really embrittled this material, oxidized this material. So what we learn is actually we have a strong influence of the microclimate in a PV module, and especially the glass has a strong shielding effect so that the encapsulants usually don't degrade that much. The power loss that we found was attributed to yellowing of the encapsulant, and even though we saw yellowing after each test, only after UV tests, this was correlated to a power loss, because we found two different mechanisms of yellowing in the PV module. So how can we possibly predict and possibly prevent polymer-related failure modes? Yeah, you can do that by choosing the right materials, and especially the right material combinations. And how do we know we have the right combinations? Yeah, you need to know your materials and really do proper testing. And that means you need sufficient accelerated weathering tests that are usually sequential or combined stress tests, which combine the different stressors that we see in PV modules. So from like humidity, temperature, UV, and mechanical loads. And you need to do testing on all levels. So not just make modules or mini modules and then do electrical characterization, but if you really want to improve your PV modules, you need to understand degradation on a molecular level and on a material level. So that means you also need to test your materials. So in my case, it's the polymer films and some laminates, because especially interactions between materials are important. To summarize, the role of the polymers in PV energy generation has been underestimated in the past, because yeah, the polymer does not have an active role in the power generation, that's the solar cells. But the choice of polymers has a distinctive impact on PV modular attributes, because the optical properties of the encapsulant are in direct correlation with the efficiency, because they define how much light is going through. Especially quality, polymers have a big impact on quality, because most infant failures that we observed in the past were caused by bad processing parameters, which actually resulted mostly in delamination, for example. And then the polymers define the reliability, because most PV module degradation modes are directly linked to polymer degradation and material interactions with polymer components. So overall, to summarize, you need a better understanding of material properties, especially of the polymers in PV modules, in order to understand PV module degradation, power loss, and let's say reduced yield over the lifetime of a PV module. And with that, I thank you for your attention, look forward to your question, and give over to Peter.
Okay, thank you. Let me see if I can get my slides running. Okay. I'm going to talk about some of the high-end UV applications that are currently available for PV component analysis. And I will mainly focus on variable angle spectroscopy and optical characterization of solar panel cover glass. Variable angle spectroscopy is mostly used for measuring transmittance and reflectance at different angles of incidence and deriving thin film properties from these measurements. It also proved to be useful for angular result scattering measurements, which are useful for characterization of TCOs and light management. So I will discuss that a little bit. I give some examples. Also an important application for the glass industry is the measurement of solar panel cover glass. I will discuss that as well. I will not go into the glass redox measurements, which is also an important measurement. It has to do with ironing glasses green, and if you control the redox state of the glass in the furnace, oxygen activity, you can shift from the iron 3+ to the iron 2+, making it less green, having absorption only at 400 nanometers, getting more transparency for the cover glass. What I will discuss in a little bit more detail are the measurements used for total transmittance and reflection measurement of diffuse and patterned cover glass. But first, some tools for variable angle spectroscopy. These are the main tools we have at the moment. The ARTA, that's the automated RT analyzer. That was development started in 1999, the first model. The picture you see on the left is the models we have since 2007. And the TAM system, the total absolute measurement system, is a similar type, more flexible, and also used for larger samples, accessory. And that was developed in another market since, I believe, 2015. And I will not discuss them in detail, but I will just show you some of the applications. I discussed in film analysis that one of the applications is to determine the layer thickness and optical contours of the materials in an optical coating stack. And the nonlinear regression is used to minimize differences between measured and calculated angular reflectance and transmittance spectra by varying the values for the thickness of the layers, but also the parameters of the dispersion models. And this example shows you a result of one particular analysis of a 3-layer coating on a float glass sample. Another example for measuring with a TAMS or an ARTA is angular result scattering, and this is a simple sample, which this one has nothing to do with solar glass. However, it is a diffuse surface of a glass, sandblasted glass. And what you see here is a profile, a distribution which is measured just at single wavelengths using the ARTA. You can also do complete wavelength scans, but this is just a few wavelengths. Where the angle of incidence was constant, it's about, I think it's 45 degrees or a little bit less. And the detector was moving around the sample just to record the intensity for different angles of different directions. So that's one of the results you see here. A typical result from one of our customers, actually they were the first using the ARTA for this. And that was for measuring the surface topology of TCOs, which are used in solar panels, in solar cells. And the idea is that if they make a sort of rough coating, if they influence the topology, you can couple more light into the solar cell. That was the idea. And these are some materials they were looking at, mostly cheap materials, not ITO. That was regarded as a very expensive material, indium tin oxide, and there's a fluorized tin oxide, zinc oxide with either boron doping or aluminum doping. And these are typical measurements they made. So they measured from 400 to 800 nanometers, mostly at different angle of incidence. And this took about 12 hours to record all the measurements with a Lambda 1050 and the ARTA, fully automated. And they use that to optimize and to get the information on the topology. Another group working on solar cells was from the Fraunhofer Institute of Surface Engineering and Thin Films. And they had a PhD student some years ago, Wilma de Walt, and she was looking into using etching and other processes on the TCOs to improve the light management in the solar cell. And she found that with this particular material, if you have these in the distribution, some higher sort of shoulders at 45 degrees, that's how you can get the maximum light coupled into the solar cell. And this was the final result of her thesis, with showing a sample, the electron photograph of a sample, for which she got the best type of results. And again, measured by angular result scattering using, at that time, the ARTA. Nowadays, also the TAMS used for that. For cover glass, you can have something similar. There has been several attempts to get more light into the solar cell, not just by the TCOs, but also by changing structuring or making a pattern on the solar cell cover glass. And one of the popular patterns was so-called indented pyramid structure, like you see here. It's a glass with, it's rolled into the glass during manufacturing when the glass is still soft. And the right picture shows you a scan with a profilometer to get some idea of how a surface like that looks like. The problem was for the glass industry making accurate measurements for that. They found out in around the beginning of the century that it was virtually impossible to get decent transmittance measurements and reflectance measurements from this. And in 2007, we had an interlaboratory comparison with several laboratories. I think there are 16 or 18 laboratories here. And these laboratories are capable normally of measuring if you have a float glass sample or just not painted, but just a flat, smooth glass sample. They usually measure the transmittance within 0.2%. If that's the agreement we typically get with this group of laboratories. But with this type of sample, it was completely off. I mean, they actually proved that with the existing tools they had at the moment, and most of them, they used small so-called integrating sphere accessories. The standard 150 millimeter accessory was widely used, and they found that they could not get good agreements for that. So we started to investigate what are actually the issues. Of course, that's one of the things we do in my company is we investigate measurement problems, find a solution for that, and then turn it into basically a spectrophotometry accessory which can do the measurement accurately. And the result was basically in the next couple of slides, but I show you one of the most important reasons for this discrepancy that has to do with the following. If you have a standard integrating sphere accessory, this shows the accessory with the top half removed. That has a spherical cavity of very wide diffuse spectral material. And with the calibration of the baseline of the instrument, you have the left situation where the beam of the spectrophotometer, without interaction to a sample, hits the target on the back of the sphere, which is normally a reflection target. That target is supposed to have the same properties of the rest of the sphere. It's the same material, but usually it's differently aged, so it does not really have the same value. For specular samples, like glass samples and thicker samples, which are not diffusive, that's no problem with reflection measurement. Even with normal reflection measurements, that's not really a problem because there is no issue if you do a reflection measurement with this one. But in transmittance measurement, you can see on the right side, if you have a diffuse sample, some of that diffusive distributed radiation hits other parts of the sphere, which have a different reflection compared to the original target. But also, some parts can be seen directly by the detectors, which you see in the bottom. There's actually the rectangular one is the photomultiplier, and the round one in the next to it, That's actually the in-gas detector for the near infrared. And these are also situated in different places, though that can result in steps as well. Because normally they should be screened from the direct beam, the direct transmittance, not only from the sample, but also from the first hit on the wall. And you see that here, some of that is not exactly screened. So this is one of the reasons, actually I mentioned two, why you have a discrepancy in results. The solution we got is we developed a new type of accessory. We needed a larger sphere for that, a 270 millimeter sphere, which is about the largest you can practically make and also handle with an instrument like this. With larger spheres, you don't have enough signal. This is basically the maximum you can get. And we made it in a way that you can do transmittance and reflectance measurements in a slightly different way. First of all, they have both the same angle of incidence. The reason for that is that we found that an important property for comparing cover glasses with the absorption in the glass, light absorption, in order to determine that from transmittance and reflectance, the measurements should be at the same angle of incidence. Otherwise, if you have very low absorption, you can even get negative absorption coefficients. If you say 100% minus the transmittance minus the reflection is the absorption, then it doesn't fit very well. So they have the same angle of incidence. Also, the detector position is in a way that they are the same. They see a similar field during the similar screening during the baseline calibration as the sample measurement. There are a few more details, but take a little too long to go into that. But in 2017, there was another intercomparison for these type of materials, and there were more laboratories involved, but only 4 really got good agreement with that. The rest were far off again because they didn't have this newer type of sphere. And there was one laboratory which is called the Institute of Solar Energy from Fraunhofer Institute in Germany, in Freiburg. They have a large 630 millimeter sphere with diode array detectors, and they worked in a different way, not with a spectrophotometer normally. They are the black lines, and the other 3 are spheres, accessories made by us. There are, by the way, 3 different designs. The Guardian is for angular measurements also, and the OMT sphere, that was the one we had, the prototype we had in-house. And NSG had, in the UK, had also one of the sphere which is sold by PerkinElmer nowadays. And what you see here is the difference in transmittance measurement if you go in 2 directions in the glass. And this is an extreme glass because it's a 12 millimeter and a 3 millimeter, which is laminated. And the foil, the PVB foil, is diffuse. So there's a diffuser in between, and it's closer to the surface on the 3 millimeter side than on the 12 millimeter side. So that has a special effect in the measurement. And normally you should get about 0.5%, roughly or less, absorption, transmittance difference in the 2 directions. And that's what we actually got. The National Fenestration Rating Council, the goal was to have it also for diffuse glazing in windows, and that's why they now have this method also put in their new standards. The one I mentioned for Guardian, the 270 sphere, that can also do directional RNT, so angular measurements of reflection and transmittance. That's quite a large accessory. This is situated in Guardian in the US. They have a research center very close to Detroit, and they have this large accessory in their lab, and they can do angular measurements. To give you just 2 examples, these are my last couple of slides. This is transmittance, how transmittance is measured with a sphere like that. On the right side, you see how that looks from above, and the blue is the beam, and all the scattered radiation in transmittance is collected in the sphere and proportionally measured with the detectors inside the sphere. Reflection measurement, that's a different situation. That is like this. That has to become, for that we need ports inside the sphere, on the edge, on the wall of the sphere, because the beam needs to go from the inside, reflected to capture all the reflected radiation. And for that, we have a series, like you can see, there's a series of ports in the sphere wall on one side that can open one by one or sometimes two together, depending where the beam, in which the angle of incidence. And it's a completely automated tool that can do all the angular measurements. Also has a polarizer inside. You can do that separately for PNS polarization. And then also do the averaging later on. So what we did is we measured some colored cover glasses for building integrated PV. They are becoming more popular now because architects usually want to have some special quality there visually. It should visibly look good. If you put on a wall of a building, put solar cells, they somehow need to have something attractive for them. And they have special demands of maybe, for instance, making the patterns of the cells invisible, so having more diffusive cover glass, but also putting colors in there. So there are several products on the market. Obviously, you lose some energy from that. And the idea is if they will accept it, if you lose less of 10%, and most of these products you see here, they reduce somewhat the efficiency, the light going into the cell, but usually no more than about 10%. And for an architect, that's very acceptable. So my last slide is about some measurements. And on the right side, you see some measurements we did on diffuse green with that typical accessory I just showed you, because we have also a prototype in our own lab, which can even handle much larger samples than the original one. And on the left side, that's actually a window glass with a diffuse PVB foil, also measured in different angles of incidence, reflectance and transmittance. So I hope I'm within my time at the moment. So I would like to give the floor to the next speaker at the moment. Thank you.
Hi, everyone. I believe there's a poll question that's coming in. Tim?
Yep, you are correct. So before we get into Christelle's portion of the presentation, we have a quick poll question. We'll run it for about a minute here, or until we get to roughly 2/3 of attendees responding. Which analysis technique are you most interested in? Some early results showing up. So we'll run this for a little bit. Any of our presenters, feel free to come in and comment on sort of the development of the poll, if you're surprised at what our audience seems to be most interested in, if this is in line with what you expected. But yeah, we'll run this for a few more seconds here, give everybody a chance to submit their opinion. Okay, we should be wrapping up. Okay, yeah, so I think we can wrap up this poll now. As we can see, kind of the top three here are IR, and then we have UVS, AA, a little bit less interest kind of after that, but I think this gives us a little bit of insight into kind of what our audience is interested in. So Christelle, I will hand it back over to you now.
No problem. This actually leads well, because obviously I'll be talking about the technologies and the pros and cons. So as you see, we have PerkinElmer quite a huge portfolio of products, including AA, IR, UV, ICP-MS, ICP-OES. My particular product line that I govern is UV and thermal. So this is where I'll be focusing on. And obviously some of the analysis, the instruments that either Gernot or Peter have used themselves in PerkinElmer. So it's divided into two categories. So you've got infrared, that's usually known as a chemical characteristic instrumentation. So we've got a variety of that. You can even down the microscope down to the little baby spectrum 2 at the bottom. We usually, depending on the instrument you use, of course, there are limitations, but there's also advantages. So it depends on the accessory you need, the type of application and measurement you require. As long as you know what you're looking for, then we can make sure we match the instrument that is required for your application. We have the remainder of the chemical characterization will be also hyphenation. So hyphenation is when you have a combination of two or more systems together. So a lot of people that use that is because one, they can afford it, which is nice, and two, but it also helps that if your samples are very small and you don't have time to either cut it into size for various applications, for various analysis, you can use that one sample and get 3-4 sets of data and try to hopefully understand your sample a bit better. Now, in this case, you're looking really at the evolved gases from your original material. So how you characterize from what has evolved in terms of characterization for your instrument. And again, things like that gives you a lot of different information and understanding of your solar panel information or your polymeric information in order to know what decomposes first while it's heated. And again, it has its pros and cons, just as usual. So a lot of them is quite quantitative. Some can have a little bit of cross-contamination, but again, if you do a good maintenance of the system, you're looking to have very good data and information. But typically, it's you're dealing with a high temperature control instrument, a well-calibrated system, and all of that is also minimized. Then we move on into more the mechanical and thermal characterization. Again, we have a lot of instrumentation that cover this side of the material characterization. So you have your UV-Vis from the usually exists in two principles. So you've got a PDA design or the double beam design. Again, or how fast you want your analysis, we have the instrument that will fit this requirement. So the middle instrument is a PDF example. So your sample will be done in less than, I believe it's 2 milliseconds. And obviously with the double beam, you're looking at a longer time to collect your data, but more sensitivity because you're being sequentially collecting that information at each wavelength. And again, it has its limitations. So for people who require fast analysis, a double beam is really not the instrument because it's quite slow, but it's the more sensitive. So it depends on how and what you want, which instrument will be suiting your application. Then we go into the thermal analysis. Again, these guys can further split into two groups. You've got your routine systems, and then you have the one for R&D, so troubleshooting system. And again, you can still use, just like at the bottom now, the image, the hyphenation system to do the same analyses. So for routine system, you're looking at people just trying to characterize the polymeric materials, discriminate between the materials, finding the resulting effects. These are robust machine. You can set it up in your auto sampler, pass 46 sample at a time, and then collect the data over a couple of days, and then measure your physical properties, so decomposition, glass transition, melting points. And then using that information, differentiating between the composition of your materials. Or you can do the problem solving where you go for the bit more gusty, more sensitive instruments. Hopefully, it'll give you, again, a more in-depth understanding. These will give you the more mechanical properties of your material. So the mechanical behavior, especially with the DMA, weight loss, long-term behavior, cross-linking properties. So it's important to select the right instrument to give you the right information to help you identify your application. And again, they have also their limitation, but the benefits. So with thermal analysis, you can get a variety of properties measured throughout using the thermal line. Some people, because we're using thermal, you can use small samples. Sometimes the small density can also be a problem, but also a benefit. Again, it depends on the application. You can identify a lot of materials, and especially material process temperatures, which is what Gunnar was also mentioning earlier. Process temperature and process information is important in your solar devices. Finding out how much energy is required to melt something, or quantifying any component that is either decomposing or not. You can do so with this type of information. And I think that's it really for all the instruments. So if you have any other question, we have Lucy next as a speaker.
Hi, thanks, Christelle. This is probably the last slide before we move on to questions. So before we take any questions, I just wanted to briefly return to the topic of sustainability. It's what was highlighted actually at the start when we watched the video. So for PerkinElmer, our message to the solar industry is really rooted in empowering that sustainability, and that is, standing alongside you and really walking that walk by infusing sustainability into all aspects of our business. In practical terms, that means, so you can see on the slide, starting with the purpley pink one there, by designing and making instruments which are sustainable by design, i.e. they might consume less energy or gases, which then go on to help our customers in the green and whole industries to innovate better solutions for the planet, whether that's making energy, storing it, or recycled materials. And finally, in the blue, by looking inward, by identifying key safety, resource efficiency, and energy saving activities that we can do to help reduce the environmental impacts of our own business. So we want to be part of the solution in helping combat climate change by embedding sustainability more and more into all we do. If you're interested to know any more, you can find out more on our website, and I've put the link in there. So thank you, and I'll now hand back over to Tim, and we can do our Q&A.
Thank you, Lucy. I appreciate the presentations from each of our speakers today. So without further ado, we are going to hop into the Q&A. The first question here is for Dr. Oreski. Is there any analysis of the degradation rate of adhesion promoters when the EVA is exposed to ambient temperatures and humidity pre-curing?
Let's say you can measure the adhesion promoters the same way we did it. So like really doing this gas chromatography, and you actually get a nice signal on them. And you could do that just right before lamination like we did. And it would be definitely, let's say, good to check, especially if you leave your encapsulants open for some time. So that means for some weeks that you check the adhesion promoters, because they usually are sensitive to humidity.
The yellowing aspects of degradation that you touched on early in your presentation, and someone wanted to know, for installed PV modules with yellowing of the uppermost sunny side backsheet layer, what testing can you do to determine if there is a valid warranty claim, perhaps on like the basis of safety?
I guess this question is addressed to me as well, because you were like, for the first seconds, I didn't hear you.
Oh, yeah, sorry.
I'm not sure if backsheet yellowing is a warranty claim at all, because in many cases, backsheet yellowing, it's a visible degradation mode of the material itself, but it usually has very low to none impact on the module, let's say, on the module power. And also very often just surface discoloration doesn't give you an indicator if your material, especially in the bulk, is degraded. So you cannot correlate that easy surface degradation or surface yellowing with like embrittlement. And then you may have a warranty case, because then you may get cracks in the back sheet and a problem if you're in your wet leakage installation, for example.
We had a question for Peter here, and that was in terms of building integrated photovoltaics. Someone was wondering, how much loss is, how much performance and conversion loss is created by using, colored or maybe some sort of patterned glass, and at what point does the issue of, aesthetically pleasing aspects of BIPV kind of come into kind of take issue with overall performance. So I guess a better way to ask that question is, is there a point where performance has to take precedence over kind of the aesthetic aspect of BIPV?
What I've seen is that because I'm just sideways involved in projects like that with many participants, and usually my company works either as a consultant of how to perform the measurements, or we do the measurements in those projects. But listening to the final presentation of those projects, I noticed that variation because you get some degradation in performance. Obviously, if you cut off some of the light with the products they are trying to get on the market, they are within 10 and 15% less performance. So you have less efficiency from that, but there are some other benefits apart from having a more uniform building and almost invisibility on a building facade of the solar cells and panels. You can make them almost invisible behind the glass like that. The other advantage is that obviously also degradation is probably less because there is more of first of all more of UV cutoff there, and depending on the color you can have some benefits as well. And the light is more diffusely spread, so it also has what I understand is it has sometimes some benefits on when there's a shadow on a building. If it's sharp shadow, it becomes less sharp on the solar cells. So,
right, and I think it might also be important to consider that BIPV is not currently like a resource that is expected to harbor huge amounts of load or provide huge amounts of electrical. It's more just an ancillary sort of application of the technology that provides generation and a uniform look, but it's not like anyone's relying on BIPV for large.
It's not about maximizing the power output of those panels. It's just about basically maximizing the usage.
Right.
When architects see something attractive in that, they become more used in buildings. And even if you have 10, even 20% less performance out of them, it's better than nothing, what is now the case. So obviously if they are the top of the building on the roof, nobody cares how they look like. But if it's in the facade, there you want, especially for architects, they want to have something which is more integrated and that the facade looks more uniform. So they want to have, if you have part of the facade is transparent, obviously, if you have those big glass buildings, and part of it is not, you can still add solar panels to that and make them a kind of invisible. So that's basically the idea. Also, currently, I don't think there are standards for that as well. There are no regulations for BIPV. I know there are some groups working on that, but currently, at least not in the Netherlands, and as far as I know, not in Germany and Belgium as well, they do not have regulations on BIPV. And not as much as you have on regular applications for solar panels.
Is my mic coming through? I was understanding that I had mic issues there for a second. Can everybody hear me?
Yep.
Okay, cool. Sorry. Question here, I believe for Christelle. For UV, Vis, and IR testing, which approach would be better? To mount your own source and then measure sample spectra, or to compute sample spectrum based on measured sample spectrum and the spectrum of your source?
Wow. It's usually, especially with solar panel, you do a bit of both because you need comparison data. So you'd use your, your source that you have computational data for, and then use the current accessory, because ideally you don't want it too far off the standard so that when it does get tested as a routine instrument, it can be copied by other system. They can go and buy an accessory and measure it. We obviously have the set accessory like Peter uses, so the TAMS and the HARTA. You've got the 250 to 170 mil sphere as well. So we do have accessories that would also hopefully mimic whatever information that you're trying to look for. So it really depends on if you're looking to do a comparison or just making sure you're validating something or just doing for research. Hope that answers your question.
Yeah, no, I think it does, and it was definitely kind of a super loaded question there, so I appreciate your perspective on that. Another question for Gernot here. Did you evaluate the change of cross-linking rate of EVA after different reliability tests? And kind of as a follow-up to that, is the aging and yellowing related to cross-linking rate change?
Let's say that way. We didn't, in this project, distinctively look on a change of cross-linking, but let's say my experience from other projects is that usually, even though the modules are not fully cross-linked, like at the beginning of these tests, at the end they are, there may be an impact on yellowing, but I don't know for sure, to be honest.
Certainly. So another question here, sort of, not necessarily for Gernot, but can you test for lead PB content in solar coatings, maybe an example, in bus bars?
Let's say, I'm not sure how much with spectroscopic tools, you can definitely test for like lead salts. So you find lead acetate with Raman spectroscopy, as well as with infrared spectroscopy. So this kind of stuff you can identify. For elemental lead, you need to do, I think, more like EDX, so like really electron microscopy or other techniques. Mm-hmm. I don't know, maybe some add-on from Christelle or so.
No, I agree. I think with that type of material, you need something a bit more with gusto, EPS, or all these XRF, XRD, X-ray, things like that. You may CPA, no, yeah, it's what happened is if there's a polymeric sample next to it, you'll see the effect of it, but you won't pick up the lead metal itself. That's what most people do. That if you can't measure directly, you can measure its effect on the component that will have a UV or an IR active part. But usually you need something a bit more like Raman, XRF, XRD, XPS, SEM. We wouldn't be able to have a direct analysis without these.
Mm-hmm. So it may be possible to, kind of assess the presence, but it's not the sort of correct test for.
Yeah. Because sometimes in infrared, if you use the far infrared, you could kind of see some of the metallic. If you got like a polymer that's next to a metal ion, you'll see something. But again, when you're in the far infrared, you're already at the limit of the infrared region. So you're already at the limit of everything with with the effect of possible metal. You can see something, but you won't be able to. I don't think you'll be able to quantify. You'll definitely see something and be like, oh, maybe something's happened, but you need to verify it definitely with another technique.
We are getting close on time here.
Go ahead, Tim.
Oh, I was going to ask one more question, but if there's something, if we have to continue on, Beatrice.
No, we just couldn't hear you again. Go ahead.
Oh, sorry. Yeah, so we are getting close on time here. So kind of with that respect, I'm going to ask kind of one more question here, and then we can move into sort of wrapping up the webinar. This last one was for Gernot. In your early slides there, you kind of outlined PERC and HJT as sort of technologies that are going to be taking over the solar space in sort of the near-term future. I was just wondering if you had any sort of timeline on when you expect that near-term future to be, or certain hurdles that need to be overcome before that can be sort of the new norm.
I would say PERC have already taken over. The latest numbers I know from the yearly, let's say, PV technology roadmap that is published by the German Association of Machining of VDMA, I think PERC already are 70% of the market. And let's say the standard ALBSF cell is more or less out of everything. And in the next years, I think what I remember, that heterojunction cell technology will increase to 10 to 20% of the whole market. So it has already happened. It's not a thing that will happen in the next 10 years, but let's say the standard solar cells as we had it the last 20, 30 years, the same architecture that is gone actually.
Great. Appreciate you answering that kind of last question here for us. And I appreciate each of you for your presentations today. I think this was a phenomenal look into kind of the future of PV module innovation. So once again, thank you to each of our presenters. Before we wrap up, we have the latest news, both print and online, for PV Magazine. We have an article by one of my coworkers, John Fitzgerald Weaver, Half a Penny for Near-Firm Solar and Trillions in Renewable Opportunities. And then an article that I collaborated on with another of our editors, Ryan Kennedy, regarding President Biden's halt on new solar tariffs for the four Southeast Asian countries outlined in the Department of Commerce anti-circumvention investigation. And just a reminder, you can get 10% off a subscription to PV Magazine with the code webinars10. And speaking of webinars, we have more coming up. So on the 30th of June, which is a Thursday, we have alleviating battery storage growing pains through quality assurance. And on July 5th, we have the pressing need for powerful storage, technology trends, safety optimization, and challenges for deployment. If you would like to learn more about those upcoming webinars or revisit a webinar like this one and visit the recording at a later time, you can do so at pvmagazine.com/webinars. There was a QR code there, but our webinars are very prominently promoted, so you will be able to find them from PV Magazine. One more thing before we head out, I would ask each attendee to fill out the survey. We use them in order to develop content that is much more in line with what you would like to see, what you would like to hear about, and we use them to make an overall better webinar experience for you, the attendee. So one more time, thank you to each of our presenters, and we hope you each have a great rest of your day.
Thank you, everyone. Bye.
Thank you. Bye-bye.